Hey there, it's Shannon Magic Myers. Happy Mother's Day. I'm here with you making another video, so you know how much I've got to love math. Anyway, today we are going over one of the last couple sections in discrete math called Matrix Representations of Graphs. Just to give you a little bit of background, at my college at this time, the only prerequisite for discrete math is pre-calculus. So in our pre-calculus, our students haven't had matrices yet. So this is just a very basic overview of how you can make your adjacency matrix given a graph and vice versa. Okay, so I hope you enjoy. Here we go. Matrices are two-dimensional analogs of sequences. And matrices, by the way, are used in MATLAB coding. There's a great program called Octave, which is like the free version of MATLAB. And a lot of the coding in that that you can use is matrices, right? They are also called two-dimensional arrays. So our first definition has an M by N, red, M by N, matrix A over a set S is a rectangular array of elements of S arranged into M rows and N columns. And it looks like this. I know it looks pretty scary, but basically this first one here, if you go to just the general Aij, right? The common way to name an entry in a matrix is the lowercase letter of what the matrix is named. So since this matrix is named A, right, we have lowercase a sub ij. So when you think about the entry Aij, the I represents the row that entry Aij is in, and the J represents the column that entry Aij is in. So here, this would be the ith row, right, going across. And then going down, you would have the jth column. And then you'd have whatever color you're using. And then where they intersect is the row and column that your entry is in. Cool, where it's circled there. So, zoom back out a bit. So we write A equals Aij in brackets. That is how our linear algebra text notates it. You can also do the representation in more of a parenthesis, but you're going to see me use this notation more often. And if you take linear algebra at our college, or you watch my movies that I am going to be making on linear this summer, you'll see that notation. Okay, so this basically means the same thing, but it's in shorter form. Cool. All right, so here we go. Just like we said, the ith row of A would be represented like this. Here you'd use a bracket. So we're in the ith row, so we'd be in A, I1, that means the ith row in the first column, the ith row in the second column, and you'd keep going on until you get to the ith row in the nth column. This is for an M by N matrix, and you close off your bracket. Good so far? And the jth column of A is, now you're going to have a column vector, and this would end up being A1J, A2J, all the way down to AMJ. And this again is for an M by N matrix. Cool, cool? All right, so the entry Aij and the ith row and the jth column of A is called the ijth entry of A. A matrix with M rows and N columns is said to have size M by N. If A and B are matrices, then A equals B. If and only if A and B have the same size and the corresponding entries of A and B are equal. So that would mean, in general, Aij would equal to Bij for all I equal to 1, 2, ... all the way down to M, and J equal to 1, 2, all the way down to N. A matrix which has the same number of rows as it has columns is called, which would be basically M equal to N, is called a square matrix. A matrix with N rows and columns is said to have size N by N, or to be a square matrix of order N. So if you had a, square matrix of order 2, you'd have a 2 by 2 matrix. A square matrix of order 5 would be a 5 by 5 matrix. If A is a square matrix of order N, then the main diagonal, which starts at the top left entry and goes to the bottom right entry, consists of all the entries A11, A22, all the way down to ANN. Cool so far? Okay, great. And this is what a square matrix of order N would look like. So notice you now have this main diagonal zone here that we can do our little ... dots on because they go in a pattern. Good so far? All right, awesome. So now we'll do an example relating to matrix equality. So, or a couple examples. So for the first one, are these guys equal? And please explain. What do you think? Well, the entries look kind of the same, but the matrices look totally different, don't they? So good, this would definitely be a no. And the reason for that is because A, it has size, what? A is A. So how many rows does A have? Good. 1 row and 4 columns, right? So A is a 1 by 4 matrix. And what is B? Good. B is a 4 by 1 matrix. We'll say that this way. B has size 4 by 1. So A is not equal to B because one of the premises was what? They had to be the same size. Good so far? Now here, in example 2, what you can see is that we have what? this first matrix is a 2 by 2, 2 rows by 2 columns, and so is the second matrix. And they're set equal to each other, are they not? So here, if we go and we set corresponding entries equal to each other, wouldn't 2x minus 1 have to equal -5? And so you can just go ahead and solve for that entry. That's one of the cool things about matrices. In this particular case, what you're solving for isn't a system of equations. It's just a linear equation in one variable. So but you'll do it 2 different times to solve for the 2 unknowns in the matrix. So 2x minus 1 is equal to -5. So if you were to isolate your x, 2x would then be what? Beautiful, -4, and x would be -2. So now we have one of the entries, and that was the yellow part. And then what else could we equate? Good. Y cubed is going to have to equal to 1/8 because they are corresponding entries. So this is like our first part of the problem, and our second part is finding the other unknown. So we would set y cubed equal to 1/8. Cool so far? So, and we got that from equating the corresponding blue entries. And now, in order to solve, you can either take the cube root of both sides or raise both sides to the 1/3. That's equivalent. So I'm going to just cube root both sides. 1/8 is a perfect cube. And then we'll have y. Remember, you do not need the absolute value of y because you only need that if you have an even index on the root. So this will be y is equal to 1/2. And we've solved it. So x is -2 and y is 1/2. Those are the values where if you substitute them back in, you will get equal matrices. Groovy? All right, so now example 3. Let's look at this matrix A and let's check it out. Just to make sure you're comfortable with this matrix, what is entry A sub 2, 3? So what would we do? We would want to go to the what? Actually, I'll do it in this. We'd want to go to the second column, which is here, and we'd want to go over to the third entry, right? And so here we're doing that because we're in the second row and the third column, right? So this is column 3, and over here this is row 2, okay? Good so far? All right. So, and actually, these are vectors. So if you have taken, you can write these as vectors, right? Or as matrices. But there's column vectors and there's column matrices and row matrices. So you can think of these things as vectors, if you will. All right? Because you can always write the vector transposed. So that's just a little preview. So it turns out that entry A23 is equal to 23. And I'm sorry about that. It's not because of that subscript being 2-3. It has nothing to do with that. That was just a coincidence. And so it's this way because 23 is the entry in the second row and third column of A, okay? So that 23, again, this 23 is because it landed here not because of the I and j representing I equals 2. So in this case, I was equal to 2 and j was equal to 3. So that's the deal with the subscript. Cool? All right. I thought about redoing it, but then I'm sure that would happen again potentially, so that's why I kept it in there. So here we go. What are the entries in the main diagonal? So if we go from the top left down to the bottom right, we get the entries 6, 0, and what is that? Negative 32. Cool? All right. So that's the answer for this one. And then the 23 was the answer for the first one. Okay, so now we have another definition. Let G be a directed graph with ordered vertices V1, V2, all the way down to Vn. The adjacency matrix of G is the n by n matrix A equals Ij over the set of non-negative integers such that Aij equals the number of arrows from Vi to Vj for all I and j equal to 1, 2, all the way down to n. So, taking a look at this one here, what do we have? Well, what you need to look at, I know it looks a little bit confusing, all right? And remember, this is a directed graph, so there definitely is a specific direction these arrows are going. And so basically what we need to know is, well, is there an edge going from, V1 to V1? Is there an edge going from V1 to V2, etc.? And you do that for all of these vertices. So you're going to need, you have 4 vertices, so you're going to need a matrix of order. Beautiful, 4, okay? So if you look at it kind of like this, and you can call it matrix A if you want. Actually, I'll make this one smaller. So basically what would happen is you're going to have your general matrix will be A11, A12, A13, A14, A21, and this is going across A22, A23, and A24, etc. until you get your 4 by 4 matrix. So this will be the general form. And, well, what does this represent? Well, you'd have vertex V1, vertex V2, V3, and V4 across the top. And then they'd also be going down. And then it would be V1, V2, V3, and V4. Okay, so the first entry is saying, is there an arrow going from V1 to V1? Well, is there? Yes, because why? Do you see we have this guy here? So that corresponds to this entry. Does that make sense? So here we would have for when we do our actual matrix, right? We would say A is equal to, I'm just calling it A. So our very first entry is going to be a 1 because there is one arrow going from V1 to V1. Cool so far? All right, how about going from V1 to V2? That would be entry A12. So is there anything going from V1 to V2? No, right? So you would just put a 0. How about from V1 to V3? Well, yes, you actually do have 1 going there. So you would have, do you see that from V1 to V3, you have edge 3 going right? And so we would put a 1. So it's either you just count the number of arrows that are going from that specific matrix to the other. So continuing, we have one of those. And then I'm going to go a little bit faster, and you can pause the movie and then check your work and see how you do. Okay, so I highlighted the corresponding arrows, and so hopefully that helps you. All right. So now what we're doing is in example 5, we're finding a directed graph that has the following adjacency matrix, and there are different ways one could draw this graph, just so you know. So here, again, along the sides here, this one also has 4 vertices. So we'll go down here. This one also has 4 vertices. So as to keep us on track, we will take a look at that. Now, again, if you have the number, at the intersection basically means the number of arrows going from the one vertex to the other vertex. Okay, so V1, there's a 0 right here, remember? So that means that there is no loop at vertex V1. Make sense? Okay, so let's do it. I'm just going to put in our vertices, and you can draw them any way you want, as long as it follows, of course, the adjacency matrix. Okay, so here we go. I'll draw the edges in different colors. So here we go. We have a 1 going in entry A, 1, 2, first row, second column. So going from vertex 1 to vertex 2, there's 1 arrow. Okay? So vertex 1 to vertex 2, there's 1 arrow. And then you might want to kind of look ahead, because if it kind of loops, if there are parallel edges, you might want to do more of an arc instead of a straight line. Just depends. All right, so then there's no other arrows that go from V1 to any other vertex. Now, going from V2 to V1, there's actually 2 arrows. So what that means is this. That means that you'd have something along these lines. And remember, this is a directed graph, so you could go something like this. I'm left-handed, so it's a little hard for me sometimes. You could have one that's like this and another that's like this. So let's name these edges, okay? So we'll call this edge 2 and edge 3, and that first one would be edge 1, because that was the first edge we did. They don't have to be named that, but that's what I'm naming them. Good so far? Blurry. Okay, so now we've gone ahead and taken care of that part of it, this one here. And then we also see that from vertex 2 to vertex 3, there's 1 arrow. So I'm going to look back, and actually, well, we'll just do it like we did before. We can always rearrange it later. So here we are. Sorry. So this one here from 2 to 3 can go like this. Just in case I'm going to do it as a curve, we can call this one E4. And then now we're on to the next row. So here on our next row, color, I guess we can use black. So from V3 to V1, we've got one line, or one edge rather. So I'll do it a little curved so it doesn't get too messy looking. And we can call this edge, what are we on? Edge 5. And then from V3 to V2, I see 2 arrows. So, gosh, running out of colors here. 2 arrows from V3 to V2. So we can do one that's curved, and we can do one that's straight. And we can call this edge 5, or edge 6 rather, and edge 7 if we want. And now, and that was, whoops, sorry, that was here. And then from V3 to V3, we do have one, so there's going to be a loop. All right, and then from, let's go on to some other colors here. So do you see that the only arrow that starts at vertex 4 and goes to something else is from vertex 4 to vertex 3? So I'll just do a straight line here. And then we've taken care of that one. So that is a directed graph that goes with this adjacency matrix. Cool, cool? I think these are really kind of fun. Call me a math nerd, but I'm feeling it. All right. So next up, here's another definition. And so we have G is an undirected graph with ordered vertices V1, V2 down to Vn. So the adjacency matrix of G is the n by n matrix A equals Aij over the set of non-negative integers such that Aij equals the number of edges. So this is more general. Number of edges connecting Vi and Vj for all I and j equal to 1, 2, down to n. I'll put in the new ones soon. Okay, so here we go. Again, find adjacency matrices for the following undirected graphs. So here, notice there's no arrows. So we'll have A is equal to, again, we have 1, 2, 3, 4 vertices. So we're going to have a 4 by 4. Okay. So, going a little more quickly, again, we have V1, V2, V3, V4, if you want to have just a little more direction for yourself. You don't have to write the V's. And we have one edge that's going from V1 to V1 because we have the loop, okay? So this time I'm going to go a little bit more quickly. So V1 has a loop, and so it's edge E1 that's there. So we have 1 going from V1 to V1. From V1 to V2, we have 0. Do you see we'll have zeros for the rest because V1 only has one edge. So V1 is only adjacent to itself. Okay, so now V2 to V1 is 0. And V2 goes to itself, that's edge 2. So we've got one edge, right, from V2 to itself. Now from V2 to V3, we have one edge. And from V2 to V4, do you see we have 2 edges, E3 and E4? So we'll put 2 there. Now from V3 to V1, there's 0 edges. From V3 to V2, do you see how you count that edge again? Even though you already counted it for entry A23. So it turns out that this matrix might be what? Think about it for those of you that have had linear before. So what about does vertex 3, is it adjacent to itself? Yes, because edge 6 is a loop there. So we've got 1. And then does V3 go to V4 at all? No. Okay, so for V4, it does not go to V1. It has two edges going to V2 because E3 and E4 are parallel edges, right? And then and we're not worried about direction this time. And then V4 has nothing going to V3, and V4 has nothing going to itself, right? So we're all good there. And so for those of you that have had some training in matrices, what do you notice about this one? Good. A is a symmetric matrix, which happens to mean that Aij is equal to Aj. Pretty cool, huh? All right. So now let's take a look at this next problem here. And this is actually our last example. So we've got the K23, the complete bipartite graph on 2, 3 vertices. And so I don't know if you remember that. I thought I'd bring this back a little bit just so that it would be a little bit of review from some of the earlier stuff in chapter 10. That means that there's 2 V vertices. Sorry, can't talk today. And then we'll call them W, right? We can say that there's 3 W matrices. And remember that for the complete bipartite graph on 2, 3 vertices, the V's won't connect to each other, but each V connects to every W and vice versa. So the W's don't connect to each other, but each W connects to V, and it's not a directed graph, so we don't use any arrows. So this is what it will look like. We'll have an edge shared between V1 and W1, V1 and W2, V1 and W3. And we'll also have edges shared between V2 and W1, V2 and W2, and V2 and W3. So that's what the picture looks like for the graph, in case you needed it as reference. And then let's take a look at what that matrix would look like. So here you would have, remember, it's got to be square, right? So we're going to just kind of sketch this out a little bit. We have to represent the V's, right? But we also have to represent these W's. And then you just go about it the same way as you did before. So notice that we now, notice that we now have a 5 by 5 matrix, and it will look like this. So do you see that we will have symmetry, right? Because if V1 goes to W1, W1 has to go to V1, right? So there's not going to be any loops, right? So the diagonals will all be 0, right? And then we'll have symmetry on the other matrices, or you can just do it one by one and go for it yourself. So I'm going to do this a little bit more quickly, and you can check your work, and we'll compare at the end. All right, have fun. Okay, so how'd you do? Pretty cool looking matrix, huh? So we'll call this matrix A, just for fun. And so this is our adjacency matrix for this graph, which again is undirected. All right. So that's it for today. I hope you have a wonderful morning, afternoon, or evening whenever you are watching this show. And if you like what I'm doing, please subscribe. Bye.